Hey, hi. So today we'll be looking at some basics of generative AI. Okay. So this is our presentation. So if you see this, this is the agenda for first day, basically, and you can see that we are about to cover what is the difference between discriminative and generative AI, right? And then we will do a deep dive into generative AI. Then we'll understand what are foundational models like Llama and Bot, what is their difference, and then we'll cover some basics of deep learning, how deep learning is different from machine learning, what is it, what is the subtle difference between artificial intelligence, machine learning, and deep learning. And then once we are done with that, then we will start the transformers. Transformer is a major, yeah, it's a major architecture which most of the modern day large language models are based out of. So yeah, let's see how transformer looks. Transformer architecture looks something like this. This is a so transformer has two stages: encoding and decoding. And encoding uh, ensures that the what is the relationship between different words of a sentence that is captured by the self-attention matrix. And you can see different components. There is thinking, there is self-attention, right? There is normalization, there is FFN, feed forward network. There are some things which are out, which are not here in the architecture. For example, tokenization and then calculating the embedding. Okay, so just give me 1 minute. I'll have to. So actually, there is a class going on for AVIT students. Okay, that's why I'm taking a break. I have to. I've already given a workshop on generative AI in this college. So then this is an extended session. I'm just signing into Teams Microsoft. Let's see. Hey, hi guys. Good morning. Just I will close this. Yeah, are you able to hear me out? I can see Meena, Jayashree, Aravinda, and Srinivasa, Durga. Can you hear me?
Yes.
Okay, awesome. So we'll wait maybe a couple of more minutes for others to join. Then we will start. So today we will do some hands-on labs on various components of transformer. That's how we'll start this session so that we can cover it end to end. Okay. And then maybe next Saturday we'll discuss the assignment. How many of you have done the assignment, that coding assignment? I received Jayashree's responses. Anybody? Okay, let's do one thing. Uh, is there any message? Okay. Who is P? Uh, okay. I did the assignment, sir. I will send in mail today. Okay. Cool, Aravind. So there are some things which we can discuss, right? Like, first of all, welcome to all of you, and it was really nice connecting with you all in AVIT. So now I think authorities want us to remain connected and uh, have these more meaningful sessions on every Saturday, 11 to 1. And I think 5 sessions have been scheduled, right? So I would like to learn from you that what you would like to learn in these sessions. Would you like to go deeper into coding and project level assignments? For example, creating your own code generator or creating your own copilot bot, or would you like to go deeper into transformers, because we covered transformer basics, but we did not really understand that how much each component is impacting the result. That is the second. And third is, like, there is one thing. Third is obviously like one way to cover these 5 sessions is to cover those topics which we could not cover completely in those 5 days. For example, MLOps, how a particular model gets deployed on production. We wrote Python code, we trained the model, right? And then we do logistic regression on that model, and then we predicted the values. But in order to, for that model which we have trained to work on production, for example, you are able to use these BERT and what do you say? Yeah, one second. Yeah. So for example, BERT is there. We have used GPT-2, right? Distill GPT-2. So all these models are actually productionized. That's why we are able to use them. So how do we productionize a model? Okay. For example, if you have trained your model, then before productionizing, there are some standard testing which has to be done. Those are known as experiments. So that is the fourth way we can do these 5 sessions. Okay. I will give you an example at Google also. Like if you try to build one feature, maybe I'll show you what. Is this recorded? I'm not sure. Okay, no problem. Yeah, so I was saying that at Google also, in order to develop one feature, they have to like do like 80% of energy spent in launching and doing the launch process and doing testing, making sure that nothing breaks. And only 20% is spent on developing the code, brainstorming, developing the design docs. So the launch process is pretty important and it takes a lot of energy actually. So one other way is to like maybe have out of five, 2, 3 sessions on this how we deploy a model on production. There are a couple of softwares which we can walk through and we can install. So these are 4 ways I can think of. What do you suggest? Which way we should start? Any inputs, Aravinda, Jayashree? Were you able to figure out? Were you able to understand what I'm saying? That there are 4 ways we can cover these 5 sessions. Somebody, okay, Radhika. Saturday is an off, right, in college, or what? What is the status there?
Yes, sir, it's enough.
Okay, okay, okay. So let's do one thing. Let's start with the transformer basic only. Okay. So, hmm, one second. So, what is the first step we do in transformer? We feed a sentence, right? What do we do on top of the sentence? The input sentence. How many of you add breakfast or what? What is happening? Okay, no problem. Should I switch? Sure. Okay, I'll switch on my video. And I would request if you also can switch on your video, so it will help me. Where is the projection? Right, okay, my camera is not working. No problem. Share. Are you able to see my screen?
Yes, sir.
Okay, Srinivas. At least one enthusiastic person is here. I'm not able to switch on my camera because there is some issue in the camera, but I would suggest all of you to switch on your camera if possible. That will make these interactions meaningful. Otherwise, like you will also pass time, I will also pass, and that is not good. Okay, so right in the first on the first day we covered these all these topics, right? What is there? This this one, right? So on the in the fifth topic, you can see that we dive deeper into transformer architecture, and this architecture consists of four components, right? First, what we do, anybody remembers? Suppose there is an input to transformer which is a sentence. I love AVIT students. Then what what happens? We do tokenization, right? Okay, I think students are just adjusting or not. Yeah, we do tokenization, right? And then after that, somebody has raised the hand, or okay, Shravani. And after doing tokenization, we have the tokens. Basically, we have the words, right? And then once we have the words, then we can basically create embeddings from the words. And there are various tokenization algorithms, yeah, like byte pair encoding, right? One second. Yeah, please try to join on time. Otherwise, I will also join late from tomorrow because, like, admitting each and every student will create a distraction. So, okay. So everybody is there. Total 9 students are there. Okay. Okay. What I was saying is, okay. Yeah. Are you able to see my any projected screen also, or how is it? Okay. Now I stopped sharing. Windows 21 windows are there. Okay. This one, right? Hmm. Are you able to see my screen?
Yes, sir.
Okay. Okay. So this was the agenda of day one, right? First, we discuss the context, right? What is the difference between generative AI and discriminative AI? Can anybody answer what was the difference? What? Why generative AI? Why not just continue living with ANNs or machine learning, artificial intelligence? Why is generative AI needed? What impact it is creating on the society? Okay. Hmm. So we discussed this image, right? So in classification, we just answered this yes or no problem. Whether a particular data point is a spam or not spam. That is a discriminative AI. But generative AI is to generate something. For example, I will tell ChatGPT, can you generate code so that I can deploy a chatbot? So it will generate chatbot code. So similarly, I will say that generate this image of nest and images. So that is the difference between discriminative and generative AI. And then first we discussed that all the fundamentals like ANN, RNN, FFN, they are very important because they form the fundamentals of all generative models, all foundation models. And some foundation models are Llama, BERT, GPT. All these they have transformer as their foundation, the basic model. And this transformer is composed of two stages. What were the two stages? Now somebody should answer. Otherwise, how will we like carry on? We can do so many things actually in these sessions, but if you are not responsive, then it will be difficult. I'll tell Agilateral today. They are not responding at all.
We have an encoder and decoder part, sir.
Yeah, encoder and decoder. And the encoder looks like that diagram, right? So it has four components. And it's not necessary that only one student will respond every time. Others also should respond. Okay. So if you see this one, you can see that there is like this is a block diagram of an encoder, and there are n such encoding layers in a transformer, and then there is a decoder part, and therefore there are n such decoding layers on the transformer. So what is the function of an encoder? Anybody? Nobody remembers or what? So the function of encoder is to understand what is the relationship between different words in a sentence. If our input is text, and if it is a multimodal input, you can feed images also, you can feed audio, you can feed videos also, right? So then basically to figure out what all features needs to be trained, that is the part of encoder first. So that's why first they okay. Is there a question? Okay, one question. Yeah. So main function of encoder is to understand what are the what is the relationship between different words, and that relationship is represented by the self attention matrix, and that self attention matrix is passed to the decoding phase also, and that self-attention matrix is used to generate the next word. So encoding means encrypting into the existing database, and then that database of matrix is used to decode and predict and generate new text. So that is the overall overview of transformer. But within encoder also there are multiple stages. First you tokenize, then you calculate their embeddings, then what you do, then you do positional encoding. Positional encoding is just a vector. You can see the green vector here. So this green vector is added to the embeddings calculated from the um, embeddings calculated from the tokens. So once you have the embeddings, then you have lost the position of that particular word in the sentence. So in order to reinstate that word into the appropriate position in the sentence, we do positional encoding. And then once that is done, then we calculate the self-attention matrix using Q, K, and V matrices. So V is calculated using K and Q. And for this, for all the mathematics, you can look at the paper. Attention is all you need. Okay. I will just. Is there a chat box also here? Okay. So in this paper, you will understand what is Q, what is K, what is V, and how they are calculated by training initially. And for every word, when we calculate the V value, then we take the K value of the input word and then V value of all the other words basically, and then do a dot product and then sum it. That is the total self attention score for any word with respect to the entire sentence. So this self attention matrix helps us to understand the semantic meaning of this sentence. So once we have the self attention, then we do some normalization using softmax, and then we feed it to the feed forward network. So today what we will do is we will do a code lab which will analyze different steps of a transformer, which will basically give you some overview, some insight into the different steps of transformer, how different steps are used, and how they impact the output of the transformer. Okay, so let's start. All of you can open your collab. Are you able to see my collab, or is it something else? Okay, I think now you will be able to see. Are you able to see the collab now? Somebody has to answer.
Yes, sir.
Okay. So the heading of this collab is measuring impact of transformer stages on model output. Okay. You can all open your code labs. And then first we install uh, the modules which are needed for this code lab, right? So what we do is we pip install transformers torch. Okay, once I think most of you might be having already. Then we will do baseline model setup. So after this, you can say baseline. So first of all, what we do is we generate a word using digital GPT-2 model, and then we will create our own transformer and compare the output with this output. So this output is called a benchmark, which is the standard. Okay. So let's use the digital GPT-2 model to generate a word given an input sentence. And then we'll give the same input sentence to other transformer model which we will create from scratch. Okay. And you can like let me know if you want me to pause or if I'm going too fast. Okay. I want everybody to write this code. So once all of you are done, then only we can move forward. Or you can take help from your friends on Monday. So does anybody know what does this from pre-trained uh, auto tokenizer does? This actually, this digital GPT-2 is a model which is fully deployed on production. So we are, as it is extracting the tokenizer which has been trained fully inside this model from digital GPT-2 model. Okay. Yeah. Is there anybody? And I think in a later class we will understand what exactly this from pre-trained does, auto tokenizer does. What are the different parameters of a tokenizer? What does it mean to extract the exact model, extract tokenizer of a model? Okay. Does this admit request come to you also, or is it only me which is coming? Request for admitting new students. Okay, I think it might be me only because I might be the owner of this code. Okay, so we are writing a helper function here. Please write this little fast. Okay. So we have extracted the digital GPT tokenizer using this tokenizer to tokenize the input prompt. This prompt we will give beneath. Okay. And actually, tokenizer, what does tokenizer do? Tokenizer actually tokenizes the input and give tokens. For example, I am Rajat. It will give first it will tokenize I am, three tokens, I am and Rajat. But each token will be given a number corresponding to the vocabulary. Okay. So for example, I might be 54th word in dictionary or in the vocabulary. Then 54 am maybe like maybe 15th. So 54, 15 and Rajat maybe 108. 54, 15, 108. So this will be the like IDs will be the output. But tensor is actually returns a vector again. So tensor is further transformation of the token ID. So you can keep noting these down, uh, these points. And these inputs, the output of the tokenizer is actually fed into the model with, yeah, and we are generating now. So that is what we do in transformer also, right? So we are simulating the transformer indirectly. First we are tokenizing, then we are feeding that prompt, tokenizing the prompt, and then we are you do you remember the sampling strategies which we used to decode? Anybody remembers? Greedy search, beam search, top K, top P. We did a collab also for that. So that's why we are using this temperature to generate the output. And then,
Excuse me, sir.
yeah,
I'm sorry to interrupt. Could you please elaborate on the temperature stuff again? I'm so sorry.
temperature stuff.
Yes, I mean, what exactly is it and why we do it? Just a brush up. I'm so sorry.
Yeah, so you tell me that what are the sampling strategies we used for decoding? What is the decoding step?
Um, the decoding step or the decoding strategies, sir?
You can start with decoding step. Like, what does decoding do?
To begin with, so we have two parts. Okay. Um, okay, we have okay. It processes masked self-attention so that it doesn't predict the future. It cannot see the future tokens, and then um, okay, we have attention nets, and then we add we have normalization layers on top of that
Mhm.
to decode what to decode the outputs that we get from the encoders, and then we put them through a linear layer and through a softmax layer to get the probabilities of uh, where the output belongs.
But these layers are not used to decode them, right? Like they are just telling you the self-attention metrics, and then they do some normalization so that the matrix is equally favored to each of the token, right?
Yes, sir.
And the decoding step is basically trying to figure out that which token should be the generated token as the predicted token.
Yes, predicting the highest probabilities of each token for the next.
Yeah, so those are different strategies to figure out that which one should be our predicted token. So the first strategy was greedy. Basically, it picked the token
Yes,
which has the highest probability. And then
yes. And then
there, yeah, then next was beam. In beam, what we did was we created five buckets, and we tried to basically do some steps on each bucket and then figure out the best token. Then there was
yes,
top K, where we
yes,
picked the top K tokens and then did
yes,
some strategy and then figured out the best token. There was
yes,
top P, where we created sets, and each set of tokens should be having probability greater than P, such sets. And any set which is having greater than P, then we select one token out of that set. And then finally there was temperature. So in
Are
temperature,
you?
yeah, go ahead.
Yes, sir. No, no, please go ahead.
Yeah, so in temperature means basically it's basically temperature, top K and top P are used together, right? So temperature symbolizes entropy. What is entropy? Anybody remembers?
Yes, randomness.
Yes. So if temperature is high, then randomness will be high. But the advantage is that creativity will also be high. And if temperature is less, then randomness is less. And that means there will be more accuracy, but it will be very boring. So
So it's a like a trade-off.
yeah, it's not really a trade-off. It depends on you that what type of text do you want. For example, I asked ChatGPT, can you generate an essay for dinosaurs?
Yes.
Can you generate an essay for spirituality? What is happening in India? Okay, so it will generate an essay. It will generate a 300-word essay, but
Yes.
it might not be true that like every sentence might be correct English wise, vocabulary wise, right? But if you give a context, okay, this is a passage from one of the books, from one spiritual book, and then ask, can you describe more about this topic, this Advaitism, something like that,
Mm.
right? Then basically it will give a very precise answer, 2 3 lines answer, and that will be accurate. There will not be any flaw in the English, right? So here you see that the entropy is less and there is more accuracy. So you can note down that there is a signal to noise ratio actually. Okay.
Okay.
Yeah. So we saw context optimization also, right? Anybody remembers that in our class, in our workshop? So that signal to noise ratio increases when temperature is lesser. Okay.
Yes, sir. Yes. Okay, sir. Thank you so much. I appreciate it.
No, sorry. It increases when temperature is less, and it decreases when temperature is higher. So it's like taking risk with the stock market, right? So no risk, no pain, no gain, no risk, no gain, right? So making
Yes, yes.
temperature higher is like taking a risk to generate more text, so that there might be some relevant text, but it might lead to some randomness, right? Creativity will be there, but it will be with a cost.
Okay. Yes, sir. Okay. Thank you.
Does that answer? Okay.
Yes, sir. Yes.
Yeah. So we are just doing standard things here. We are basically creating a tokenizer, stimulating the transformer model. First, we are encoding, right? First, we tokenized it, then we use those tokens to generate the output, and then we decoded the output. So this is our transformer, and we are giving prompt as artificial. You cannot write down this code because after this, we will be running other models also, and that will call this helper method. Okay, so please write down if you really want to play around with different stages of transformer. And I think we did a code lab also on the sampling methods, right? And we were able to see output in temperature. When temperature was less than 1, it was less text. When temperature was greater than 1, it was very huge text, but a lot of creativity was there. And the text was repeated also in many situations. Yeah, so you can see that it is giving output. Artificial intelligence will be able to predict the future of the world. One second. and it will be able to then it is repeating again. So this is because temperature is 0.7 actually. If you increase this temperature, then you will have better output, but less English correct. Yeah, now I think it is the same. Yeah, so it is repeating the same thing 2 times. But at least what it is doing is the input prompt was this, and then at least it completed the input prompt. That artificial intelligence will be able to predict the future. So this is our transformer model. And now what we will do is we will write every step. First, we will find out the tokenization impact. Okay, let's make it this experiment one, tokenization impact. So tokenization defines how language is broken into units. Bad tokenization means bad understanding. So does anybody remember what type of tokenizations we discussed in the class? Or anybody wants to answer what is tokenization? Aravinda? Aravinda is there?
Yes, sir, I'm there.
Yeah, tell me what is tokenization?
Tokenization is convert sentence to numeric groups, numerical vectors.
Vectors directly?
No, sir, first we will pre-process by
Sir,
removing stop words.
can you come again? Last sentence?
We will pre-process the transform.
We will pre-process and basically we will tokenize like just like in Java. In Java we have a tokenizer, right? Yeah.
Yes, sir. We will remove stop words.
Yes. Yeah, yeah. Go ahead. Go ahead. So we'll remove stop words. We'll do the cleaning of the input sentence, right? And then finally we tokenize.
Yes, sir.
And what does mean? What does it mean tokenizing?
Convert words into tokens to understand for the computer.
Yes. Based on what? Convert words into tokens based on what? Huh? Based on vocabulary, right?
Yes, sir.
And how do we build that vocabulary? So we discussed three types of tokenization algorithms. First was character tokenization, in which the vocabulary is the entire alphabet. Vocabulary is fixed, only 26 mappings are there, right? A is mapped to 1, B is mapped to 2, like this, Z is mapped to 26. What is the, but what happens? Suppose there is a thousand GB paragraph. What will be the output? How many tokens will be generated in character tokenization? Can you answer? How many of you remember what was character tokenization?
We break the text into individual letters.
Yes. And then as you can see
So
that,
basically forming a tree.
yeah, go ahead, go ahead.
Basically forming a tree of that where we have 26 roots and branches.
Tree,
The tree that you told us about, the graph.
graph.
One more another. No?
No, I didn't
It's just
understand the tree part.
we start with A, B, C, D, and then further down the A, we branch it into B, C, D, E, F, G. Then further down B, we branch it. It taught us that.
Yeah.
It has only 26 nodes, and that's why it's not sufficient. No?
Okay, yeah, okay. But I didn't understand the tree part, but generally vocabulary means every every letter or every word is mapped to a particular token ID, right? And in character tokenization, we map every letter to a token ID. So there is no tree here. Tree is a binary search tree which is separate. There is tokenization doesn't link with trees at all. Okay. Trees can be used to that is a trie actually. I think what you are describing. In trie we stored words. Maybe I'll show the presentation once again. We should not confuse about these things. Otherwise, it will be difficult. Mhm. So this is character tokenization. Can you see it? Are you able to see?
Yes, sir.
Yes, sir.
Yes, sir.
So you can see that every letter is being converted into a token ID because we have a fixed vocabulary. A is mapping to 1, right? B is mapping to 2, C is mapping to 3, like this. Z is mapping to 26. So this is the vocabulary. So what it does is it takes the input string, it then uh, does a for loop, it removes the spaces, and then it scans the entire string character by character, and then we have a map which is known as vocabulary, a dictionary in Python. Then we translate every letter into corresponding token ID. That's why H is converted to 8, E is converted to 5, L is converted to 12. So this is called character tokenization. Okay. And Jayasri, can you can you elaborate a little bit more what you were saying? Was it this what you were saying?
Yes, this one. I'm so sorry. This one. I was being blunt, I guess. This one. This exactly one.
Yeah, this is not tokenization.
Oh, okay. Then this. Acha. No, sir. But I see. I think I was mistaken. I'm sorry.
Yeah, no problem. So we took this example to demonstrate the three stages of a large language model. So first, large language model is pre-trained and then it is fine-tuned. Then it is given some prompts to further fine-tune that fine-tuning. So we took an example of try that what is pre-training, inserting all the words which is on the web in the try. That is like pre-training because your try will contain then the million and trillions of words which are on the web. So once we create that try, then we can fine tune it. Suppose there are words which are starting with R or S which are very huge. They are in millions, and words which are starting with Z they are in hundreds. So we will fine tune the storage for each letter, and finally we will do some prompting. We will say give me all words starting with A, then it will traverse the subtree which is starting with A. So this is a data structure trie which is very much used by in the industry, and the main feature which is powered by this data structure is auto suggest. As you type in Google search, right? Suppose you type D DAD, then it will give all that DAD, all the words which are starting with DAD. So this is try. This is not exactly tokenization, but it is basically a data structure where every node is a character. Okay, tokenization means since the models they don't understand words, so every word is converted into a token. And what is the downside of this character tokenization? Can anybody answer? Nikhil is there today?
There's only 26 one.
Sorry.
We have only 26 letters, so it's not quite enough of a context.
Oh, wow.
Oh,
No, this is
is
not
that
the answer.
uh,
Enough for the context. We are not calculating context at all in tokenization. A context.
no? I mean, we have only 26 letters,
Hmm.
so it's too small to the the range is too small. The bag of letters is too small.
Why? Range is too small for what? Too small means good, right? We will have lesser memory usage. Why is it bad? See, that's what I'm saying. That in algorithms, data structures, machine learning, you have to be very specific. If you don't know the answer, you don't know the answer. It is either zero or one. If you are given a very hard problem to solve, like LRU cache, then you can do some attempts. But in these types of questions which I am asking, you will have to be very precise. So here, what will be the output? How many token IDs will be generating?
So is vocabulary size the correct word?
Yeah, that is a correct word. But
Okay, so we have very small vocabulary size.
but is that an advantage or a disadvantage?
That's a disadvantage, no? Because
Because
when you have, because you won't be able to predict efficiently what comes after one letter. That's
but
too tedious.
prediction is not the job of tokenization, right?
Uh, okay, I don't know. Sorry.
No, it's good actually. At least you are saying, right? At least you are trying to figure out, and there is some confusion in your head with respect to different stages of transformers. But all these are independent stages. Are you getting it? Tokenization is independent. Converting a token into a embedding is independent. Okay. So, like you can't. So, what is the answer? Okay.
Excuse me, sir.
Yeah.
So, as we are dividing these all tokens into small units, and it will cause to a long sequence, so
Ah.
processing speed also get affected, I guess.
What gets affected?
The processing speed of transversal as
Processing speed of transformer.
transversal connecting of the tokens, picking
Ah.
of the
So
tokens
the
because
time.
of the dividing into very small chunks.
Ah. So the time complexity will be more. You are saying.
Yeah, yes, sir. Sorry for elaborating this much. The precise word is time complexity.
Yes,
To
yes.
be practical, yeah.
All of you need to work on your data structure fundamentals. Very bad. I have seen, like I have given this training in 3 colleges. I'm telling you, yeah, it's not up to the mark. I'm really sorry to say. And it's not all about machine learning in your career. Machine learning is made out of the basic string manipulation algorithms only. So please, I would suggest all of you to revise your data structural fundamentals. And there is a very nice book known as Corman, which you can consult to understand what is time complexity, memory complexity. So I think Balaji has answered correctly that if like we have only small vocabulary, then time complexity will be huge, and even the memory complexity to store all the token IDs will be huge, right? You if it is 1,000 word, every word on an average is 7 letter long, then you have to store 7,000 token IDs, right? So in order to solve this, we use word tokenization. What we do here is we have a huge vocabulary where every word is mapped to a ID, which is the position of that word in the dictionary. Okay. And then the number of token IDs which are generated are only the number of words in the sentence. So, which are only 5 in this case. And otherwise, in character tokenization, it would have been at least 50 here. But what is the disadvantage here? Yeah, now you can answer. I have like sufficiently explained, and you have attempted also correctly. What
So
is it?
yes, sir.
Ah,
So according to me, it will slow down the training efficiency, sir, due to the complexity of memory and time, space complexity and time complexity.
yeah, space complexity because of what?
Uh, Specific allocation for the token reference area.
No, you can just say space complexity because of the large vocabulary.
Large account, yes, sir.
You have to store 1,70,000 words in a map.
Hmm.
So, what is the time complexity of accessing a key in map? Map is a key value pair, right? Suppose you know the key, then you can get the value in how much time?
I don't know, sir.
O of one only. It's like a table.
Oh, fun, yeah, yeah,
In
yeah, yeah, yeah.
in SQL we have primary keys, right? If we know the primary key, then we can fetch the all the values of that particular row.
Yes, sir.
Okay, don't forget your fundamentals. Somebody is there or what?
Sure, sir.
Okay, okay. Thanks, Balaji. Yeah. Okay, is it clear, Jayashri? Now you will not get confused. What is word tokenization?
Yes,
Okay.
sir. Yes,
Yeah. So word tokenization memory needed is high, and in character tokenization, time complexity is also high, and the memory complexity of the output is also high. So that's why we decide a midway, which is called subword tokenization. And there are various algorithms here, byte pair encoding. We walk through the this example. We first filled all the individual letters which are there in the sentence in a training sentence: A, B, C, D, E, F, and R, T, and null. Then we figured out all the two-lettered words which are appearing in this sentence and then calculate their frequency. So can you tell that how would you calculate the frequency of a two-lettered word in this sentence? Anybody can tell? Or for example, D space is occurring 7 times. One, two, three, four, five, six, 7, 8. No, it is 8 times. Why 7? One, two, three, four, five, six, 7. Yeah, maybe they are wronged it. I remember asking the same question in the class, and I think you all of you answered that. How many such two string words are there, which are continuous in this sentence? Anybody? Okay, no problem. So basically, somehow we'll calculate this frequency, okay, of these two-lettered words, and we will see that D space is the two-lettered word which has the highest frequency. So we will insert this word also in the vocabulary. So what will happen is that D space will become a single token. Right now there are two different tokens, D and space, but now D space is inserted into the vocabulary. So it will look something like this. You can see the lines are joined. And similarly, we'll continue this process for a three-lettered word. After D space, which one is the three-lettered word which is having highest frequency? For example, ED was the one. Then we have ED space. So then we combine ED space also as one word. So like this is called subword tokenization, where we make tokens out of frequently occurring two-letter, three-letter, four-letter word, and we insert them into vocabulary. And that's why, okay, how? One second. Sharing, I cannot change the page. Huh? Interesting. So can you see the code lab here? This simple tokenization example.
Yes, sir.
How many of you have written this code? At least the tokenized part. Can you write this code? You can see, right, that this is the input, and we just tokenized this input, and we can see that these are the output tokens. And when you print the IDs, these are the IDs. Okay. So every token is a subword. It's neither a character nor a complete word. It's a subword. So transformers are. So here I think padding is done. Here also padding is done. So wherever there is space, there is padding. Powerful models. So at least you write this code, and will. This is the first step of determining the impact of tokenization on the output of transformer. So at least write this code. We'll go to the next step after this. So once you are done writing this tokenized code, can you raise your hand? I don't see any hand. There's only 5 lines of code. Am I audible? So this was task A. Spend tokens. Okay. In task B, we will modify input spacing and one. So what we will do is we have not one prompt, but we have four such similar prompts. Am I audible to all of you? Are you there? Or is there some connectivity issue? Hello. Good afternoon. Yeah, somebody has to respond. Okay. So we are generating text for four different prompts, and this is the answer. Wow. So the normal one, create a new generation of people. This is the first. With a lot of spaces we have here, more space will be able to detect the presence of a specific type of. And the hyphen one will more than just search for the word. Okay. So what you have to do is you have to see that how many tokens are generated. Is the length of the output changing here? Second is how much is the meaning relevant, the meaning of the generated prompt, and how much is the English correct. So these three, you have to evaluate these three prompts. So we can see that output fluency will be used to create a new. Their output fluency is there. Here we'll be able to detect the presence of a specific type. Output fluency is there. Do more than just search for the best people. Output fluency is here. So in all three output fluency is there. Meaning drift. Meaning drift means I think which is going away from the original meaning which we want to generate. First one, there is no meaning drift. Presence of a specific type of object. I think this is something irrelevant. This has a complete meaning drift. So basically, if there are a lot of spaces, then the output generated also is not irrelevant. And here, if you use hyphen, it will be able to do more than just search for the list. Yeah, this is also okay. And first, third one is token count changes. So you can even print token count maybe here in generate text. Okay, let's skip this one. So next two topics which we want to discuss is how does token boundaries change semantics and why does token granularity matter? So this will be illustrated by the positional encoding lab. So let's try to figure out what is positional encoding by writing code. Embeddings and position. So embeddings they convert tokens into vectors. Positional encoding preserves the word order. So let's inspect the embeddings. So this what is WT is can anybody figure out by Google search? Yeah. So if you print the shape, this so the model is digital GPT-2. We figure out the transformer from that model and then we get the positional encoding weights from that model. Then sorry, not this is not positional encoding, but this is the the output of the embedding algorithms. So when we search for shape, yeah, yeah. So these all these embeddings are the vector representation of each word of this sentence. Yeah, artificial intelligence will. So there are four embeddings because there were four tokens. You remember? Yeah, this is okay. This is different. Yeah, so four tokens are there. So second task is shuffling the token order. Yeah, so there is a particular order in which we have these tokens, right? This, but if we, yeah, what is the value of prompt here? I think it is the last. Okay, prompt. Yeah, this one is the value of prompt. So first we tokenize this prompt. We can see this input. So we are tokenizing these inputs, and we can print actually their inputs. So you can see that these are tensor vectors. Sorry, tensor means the ID which is created. If you remove this, then you will just get the tokens of the input prompt. Yeah, you can just comment this if you want to see that tokenized tokenized prompt. Hey, why is it printing this one? Attention mask is this. Yeah, I think this output is this only. And if you want to convert token to IDs, convert ID to tokens you can do, then it will be converted into tokens. Okay. So you get tokenize will generate tokens, but here we are having tensor only. So it is directly generating tensor. So this is a tensor actually. Okay, so let's see how we can shuffle these tokens, the output tokens. So we will pick up some random token dot rand per length of input IDs. Yeah, so this function will just generate any random number between 0 and the length, and then it will fetch the random token. These are the input IDs, these are the four. So once we have selected it, then we will unsqueeze it. What is unsqueeze? Let's see what is unsqueeze. This is int. Okay. तो इनपुट से क्या करें? Input IDs is an array. It is not int. नहीं man. अच्छा ये इनपुट्स है. ओके, सो इनपुट्स का जो इनपुट आईडी है दैट इज अ टेंसर. तो इनपुट्स का जो इनपुट आईडी है टेंसर है, उसका 0 है. हाँ. हाँ चल रहा है ना. तो शफल्ड को जब अनस्क्वीज करेंगे तो ये आएगा 4430. यहाँ पे हमने देखा कि हमने कोई भी रैंडम सेलेक्ट किया, उसको अनस्क्वीज किया है ना, रैंडम नंबर को सेलेक्ट किया तो 4430 स्टार्टिंग में आ गया, फिर 481 आ गया, फिर 9542, फिर 8001. तो ये ऑर्डर चेंज हो गए टोकन्स के शफल करने के बाद. मतलब ऑर्डर चेंजेस आफ्टर शफलिंग द टोकन. ओके. So let's see what we are doing here. Now we will generate the output token by this shuffled tokens. Let's see what it generates. तो ये प्रिंट हो गया. उसके बाद हाँ ये देखो, जैसे ही हमने टोकन ऑर्डर को शफल किया तो ये पूरा आउटपुट भी पूरा शफल हो गया। विल इंटेलिजेंस आर्टिफिशियल इंटेलिजेंस टेक्नोलॉजी, तो ये पहला ही टोकन हो गया। So this you can see, actually this is indirectly telling that if we don't do positional encoding, what will happen. Well, we have just shifted our token. Initially, the token order was this 8001 9542 4430. Now we brought 48481 in the first. Then 444 we have reversed 8001. ठीक है. So पूरा मतलब will intelligence सबसे पहले that is coming before. So that's why positional encoding is very important. Yeah. So the conclusion of this experiment is order description is degrading logical output. ठीक है. And there is a way to nullify positional encoding. So in this we have just the input token order is shuffled and then we generated the output and it is scrambled. So we are just figuring out different stages of transformer. What if we remove one of the stage, then what is the impact on the output? Another way is disable positional encoding. We can disable it by putting model.transformer.wpe.weight.data multiply all data will is multiplied by 0. So then the positional encoding becomes. So let's see what does it generate. Prompt was that only artificial intelligence will this. There is a prompt. So this is the prompt into artificial intelligence. So let us see how does the generated response looks after disabling positional encoding. Yeah, see, will be art. So there is a okay. Yeah, anybody wants me to like pause or focus on any specific thing till now? Okay, then we'll proceed. If nobody wants anything. Okay, next one is most important, figuring out the attention mechanism one. Till now, what we have tested is tokenization and positional encoding. Next step is testing the impact of attention mechanism. How does the output looks like with and without attention mechanism? This actually will take more time. Today we have half an hour. Should be able to complete it. So first we will print the matrix of attention. So when we are tokenizing, first we produce the output tokens. Then we feed the output tokens to the model to generate the output output token. This is the same as what we have done previously. Output attention. Yeah, so the attention is outputs dot attention. Then we can print. So this will print the self attention matrix of the output, how much attention which word is having in the sentence. Which remember it is calculated by calculating its relationship with every other word. So you can see it in bunch. Okay, this is also input IDs. Oh, okay. Input IDs is not none. अच्छा ये common है. So actually, this prints the number of attention layers in this particular model. It is a tuple of root tensors, but why is it getting? ऐसा. So you can see there are 6 attention years. And now we will plot the attention map. How does the attention map looks at each of these link? Oh wow. Attention is empty. Oh, interesting. कई केसेस में ऐसा होता है. In some cases, output attention is disabled by default. So that's why we have to. There are 2 stages in which you can specify to enable to output basically to debug the attentions matrix. One is the configuration when you initialize the model, and second is when you calculate the decoded out. So when you initialize the model, let's see. It is giving. Yeah, now it is giving. See, this is the attention matrix. You can see there is a gradient function tensors are also given. So there are 6 layers of attention matrix, and you can see that first layer has 4 vectors. So this has, I think, six. For artificial intelligence will is broken down into 4 token IDs. That's why every token ID has its attention vector for each other word. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 such. Yeah. Then there is a tensor. Hmm. So let's see how it plots. There are, I think, this attention matrix is calculated after every output of. Let's see how the heat maps look. Yeah, see, this is the heat map. Wow. So when you plotted the attention matrix, layer attention of -100. So how many of you are able to plot this heat map? Nobody? Can you please plot? For that, you need to get the right attention matrix, which you will get from this code. Okay, if we remove this, then. So here you have to enable attention at 2 parts. One is initializing the model, and second is generating the output. So the number of attention is 6, but when you print attention, it prints a big matrix. So I think it's a 3-dimensional matrix, right? This is the first dimension. In first dimension itself, it's a 2-dimensional matrix. So this is one 2-dimensional matrix. This is the second one 2-dimensional matrix. This is the third one 2-dimensional matrix. And this is the fourth one, this fifth one, sixth one, seventh one, eighth one, ninth. So it's like this, there are 12-dimensional matrix, and then there are 2 close brackets. Ah, it is closed here itself. Okay. But here also it is closed. Okay. Let's try to understand. Okay, here there are 2 things. Okay. So actually it's a 4-dimensional matrix. This attentions. Okay. As the first element, they are having 12 2D matrices. And after 12 2D matrices, there is a gradient function, which is softmax backwards. Okay, then it has one more tensor. So I think there are 6 such tensors. In each tensor, there are 12 2D matrices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So this is the second tensor in which there are 12 2D matrices. Okay, it ends here. And then again, this is the third tensor, which has 12 2D matrices. It ends here. This is the fourth tensor. Okay. Then this is the fifth tensor. Then this is the sixth tensor. This is the last tensor. Okay. Now we are done. So in each of the tensor, the gradient function is softmax backwards. So what here we are doing is, oh wow, this is a 3D matrix. Out of these four dimensions, we are picking up the first one, and then we are plotting it on the heat map. So how different vector is waiting. Who is it? Prasad. Okay. Lohit has joined. So we have plotted one of the, you can say one of the collection of 12, uh, right? So this one of the collection of 12 2D matrices in this plane. So you can see that one square is red, one square is pink, then there is dark pink, then there is orange. So these are the attention matrices. So the color signifies the value of that pixel, and rest of the two are the coordinates. So at 1 comma 2, it's 0 point. Like this color is somewhere here, right? 0.1. So like this, yes, able to. Okay, so let's see how we can restrict mask attention. This is the last. So we are making all the values in attention mask matrix as 0. So this you can say this is mask attention. And then we calculate output after masking all the attention. Let's see what. So the attention has been removed totally. What will be the output? So this is the generated token from the input tokenized tokens. So attention mask has been marked to 0. Okay, once like this, and then attention mask once. Okay, acha. We'll have to reinitialize the model, I think. Here we initialize the model as GPT-2, right? ये वाला जो मॉडल इनिशियलाइज किया था इसको दोबारा पिछले वाला मॉडल ही बनाना पड़ेगा. ट्राई करके देखते हैं इसमें. ठीक है, चल रहा है, जनरेट कर रहा है. बी अ मेजर फैक्टर इन द फ्यूचर ऑफ द यूनाइटेड स्टेट्स. वाह, अटेंशन हटा दिया तो बहुत बढ़िया आउटपुट दे रहा. सही है. तो इसमें ऑब्जर्वेशन क्या क्या करना है? इसमें दो चीज़ें ऑब्जर्व करना है तुम्हें. यहीं पे लिख लो ये वाला अटेंशन वगैरह सब में. From rewards, loss of early context influence, reduced coherence. ठीक है, तो अभी आज के लिए इतना ही करते हैं. अभी लोग आ रहे हैं. ओके. So I'll keep it like this. Anybody has any questions? Are you able to follow what we are trying to do? मतलब we are trying to analyze different steps of transformers. What nullifying them or making them zero, what impact it has on the output, on the predicted words. Okay, maybe I will share this lab with all of you if possible. I don't know how will I share it, but maybe to Udayam I will share. ठीक है. Any anything else? Transformers. Okay then. Thank you very much for joining, and have a good weekend. Saturday. Oh, there are people joining now. I don't know. Maybe, maybe for some other class. Hmm. Okay. Take care. Bye.